Next example, again, deceptively simple looking, calculate the pH of a 1.5 molar solution of lithium cyanide. So for this problem, we're going to do something very similar. We're going to say if we start off with lithium cyanide, what is that going to produce if it dissociates? If it dissociates, we're going to end up with Li plus Cn minus. And so if we remember our polyatomic ions, we remember that a Cn is a single minus sign, so these have come together in a 1-to-1 ratio, so they've given us the correct molecular formula. So in any case, these are the two ions that are going to form. So the next question that we want to ask is what's going to happen when each one of these ions tries to interact with water. So if lithium, Li+, comes in contact with water, H2O, the only way it can neutralize itself is to grab an OH. If it grabs an OH, it's going to become lithium hydroxide, and it is going to leave an H+, right? So if we pull an OH off of water, all it leaves is an H+. So we have to ask ourselves, is this going to happen? LiOH is strong. It's on our list of strong bases, and so that means this is not going to happen. We are not going to form lithium hydroxide because that always stays dissociated in solution, so that means that we are not going to put H pluses in the solution. We are not going to be weakly acidic. So now let's consider the other option. We also have a Cn minus. With that Cn minus, what happens? We bring it down a line and it interacts with water. So a Cn minus plus an H2O has the potential to interact with water and pull off a proton in order to become neutralized. So that would form CNH or HCN. And so if we pull off that proton, that is going to leave an OH minus. So then we ask ourselves, have we seen HCN or CNH on our list of strong acids and strong bases? No, we have not. That means this is going to be a weak. If it's weak, that means that yes, this is going to happen in solution, and so yes, we're going to make OHs. That means that this is going to be a weakly basic solution because you are now putting some OHs into solution. So now what we have to do is we have to say, great, we have made this CNH. We need to look up some information about that compound. So if we look up that compound in the back of the book in one of those appendixes, what we're going to find is that we can find a Ka for this molecule, but we are not going to be able to find a Kb. So we're making a basic solution. We're interested in Kbs, but all we have is a Ka. But we can work with that. We can convert a Ka into a Kb. So we bring this molecule down. We know that CNH has a Ka that is equal to 4.9 times 10 to the minus 10. I'd either have to give you that or I'd have to give you a table so that you could find it, because currently that information is in the back of the book. So what we really want is that Kb, but that's good. We can get a Kb from a Ka. Kb, if you recall, is going to be that Kw divided by a Ka. So that means it's going to be 1.00 times 10 to the minus 14 divided by the Ka that we just looked up, 4.9 times 10 to the minus 10. We solve that. The Kb is going to be equal to 2.0 times 10 to the minus 5. All right, so now we have a Kb. What I would like to do is to say, great, if we are going to make this weakly basic solution, let's go ahead and make that balanced chemical equation at the top of an ice table. I am going to say that Cn minus plus H2O is going to form CnH plus OH minus. So we remember in our ice table, we have these different categories. Initially, we had 1.5 molar Cn. Water doesn't count in our table because it's a liquid. We started off with 0 of our two products. We're going to form products, so plus x and plus x because there's no coefficient out front. 1.5, we're going to subtract The x, we're going to bring everything down to the equilibrium line. 1.5 minus x, 0 plus x is just an x, 0 plus x is just an x. So great, so now we have an ice table. Now we have a KB. Now what we need to do is set up that KB equals 2.0 times 10 to the minus 5. It equals that equilibrium expression, which is our CNH concentration times our OH concentration all over the reactant, Cn minus concentration. We can use our ice table to fill in that information. We're going to have 2.0 times 10 to the minus 5 equals x times x over 1.5 minus x. And so this hopefully looks very familiar to what we just did on the last problem. We're going to need to try to get all the numbers and x's on one side equal to 0. So that means I'm going to have my 2.0 times 10 to the minus 5 times 1.5 minus x equals my x squared, right? X times x. So that means I need to move everything. I need to actually distribute, right? 2.0 times 10 to the minus 5 times 1.5, and then also times minus x. And then I need to get all this on one side, so it's equal to 0. This is telling me that I need to use a quadratic equation solver in order to solve this. I'm going to end up with two answers. One of those is not going to make sense. One of those, if I plug them into my equilibrium line, is going to give me a negative concentration, and so that won't work. And so we're going to select the one that's going to give us the positive concentration in this case, and so that is going to give x equals 5.52 times 10 to the minus 3. So this is going to then go back up into our final line, and I'm going to change colors so that it makes it visible, and so we're going to have 5.52 times 10 to the minus 3 and 5.52 times 10 to the minus 3. I really want to eventually get a pH, but right now what I have is an OH concentration. So I am going to say that a POH is equal to the negative log of my hydroxide concentration. I just solved that, and that is going to be negative log of 5.52 times 10 to the minus 3. That on my calculator is going to give me 2.26 to the correct number of significant figures. But what I really want is a pH. pH is going to be 14.00 minus POH. So that is going to be 14.00 minus my 2.26. That is going to give me a pH of 11.74. And so that is going to be the final answer, because this question was all about calculating the pH of this solution. So the previous example was an acid. We were able to directly get to the pH. Here, we had a solution that was going to be weakly basic, so we ended up with a POH, and then we had to convert that into a pH. We have some of those steps written out for you. We had to get the Ka. From the Ka, we got to get to the Kb. And then once we had the Kb, we could go to our ice table, we could fill it in. We have to use the quadratic solver. So it's very important that you familiarize yourself with how to come up with a quadratic equation and then to set that up so you can solve it for x. Hopefully you're doing that on your calculator. Hopefully you on your homework are doing that on the internet if you're not doing it on your calculator, because that is not a fun process to do by hand, but very important, as you see, for the types of problems that we're solving. So there's one more example. This one is even crazier looking. And so with this, it's going to be those exact same steps as previously, but this is a molecule that you probably have not seen before. So when you look at this molecule, where are you going to break it apart? If we're talking about things that are going to dissociate in solution, we should be looking for things we recognize that break out into ions. And so hopefully you were looking at this and thinking that maybe this NO3 looks like something that would be a polyatomic ion, negatively charged, it's on the back end of the molecule, and so that means that this thing you probably haven't seen before is out there in the front. And that is in fact what we want to do. We want to break this into this part and this part. NO3s are minuses. You don't see multiple NO3s, so that means that this thing out front has to just have a +1 charge to go along with that single -1 charge. So now we have an idea of how we're going to break this thing up, and so that's been our first step many times now. It's going to be to take that and say C6H5NH3, NO3, should dissociate and give me C6H5NH3s plus some NO3 minuses. So let's think about the way these ions are going to interact with water. Let's start off with the easier one. If I have NO3 minus plus H2O, it has a chance to neutralize itself. NO3 grabs a proton, becomes HNO3. If it grabs a proton, it's going to leave OH minuses. We ask ourselves, is this strong? Yes, it is in fact strong. That is nitric acid, so that means this is not going to happen in solution. We are not going to make OHs. This is not going to be weakly basic. So then let's run through the other option. Our other option is this molecule. What happens when it interacts with water? C6H5NH3 plus. When it gets together with an H2O, it has the option to unload one of those protons to become neutral. If it unloads one of those protons, it becomes C6H5NH2, and then that H2O, it becomes an H3O plus. We look at this molecule and say, now we've got this nice neutral compound. Is this going to be something on our strong acid, strong base list? It is not. That means it's going to be weak. If it's weak, that means this is going to happen in solution. If this happens in solution, we produce H3O pluses, and if we have H3O pluses, we have a weakly acidic solution. All right, so we're expecting this is going to be weakly acidic. The next step is to think about the Ka or Kb that's associated with this molecule that we just became as this neutral compound. We look this up in the back of the book in one of the appendices, and what we find is that we can get a Kb for this molecule, not the Ka that we really want, right? We're making a weakly acidic solution. It would be good to have Kas, but all we could find is a Kb. So C6H5NH2 is going to have a Kb equal to 4.3 times 10 to the minus 10. I'd have to give this to you or let you look it up in the back of the book. I can convert that Kb to a Ka by saying that Ka is going to be equal to Kw divided by the Kb that I have. So that is going to be 1.00 times 10 to the minus 14 divided by that Kb I just looked up, 4.3 times 10 to the minus 10. I do that calculation, the Ka that I come up with is going to be 2.33 times 10 to the minus 5. So now that I have a Ka, let's think about how I can use that Ka information in an ice table. I'm going to go back and I'm going to rewrite this balanced chemical equation, C6H5NH3 plus the H2O. It's going to set up an equilibrium system that makes C6H5NH2 plus those H3Os that are making this into a slightly acidic solution. So I look at my ice table. I'm going to need to have those rows that I always have. In my ice table, the water is not going to count. I'm going to start off with 0.50 molar. I'm going to start off with 0 of my products. I'm going to make some products. This reaction has to go forward. I am going to subtract reactants as I move forward. That means 0.50 minus x at equilibrium, and x and x. I have a Ka that I just calculated. That Ka is going to be equal to 2.33 times 10 to the minus 5. It's going to be equal to that equilibrium expression where I've got my C6H5NH2 times my H3O plus on the top, and on the bottom I'm going to have my reactant C6H5NH3 plus. I can fill that in with the information from my ice table. So 2.33 times 10 to the minus 5 is going to equal x times x over 0.50 minus x. So again, just like before, I'm going to need to try to get everything on one side. I'm going to have 2.33 times 10 to the minus 5 times all that stuff on the bottom, 0.50 minus x. That's going to be equal to my x squared. So that means I'm going to again have to distribute. I'm going to have to have my x squared. I'm going to put all this stuff on one side. I'll have a number in front of an x, and an x squared equal to 0. That's going to allow me to set up my quadratic equation. I'm going to solve with that quadratic equation solver. I'm going to get two solutions for x. I've got to pick the x that makes sense with the numbers that I'm working with. And so the x that I'm going to get that is useful is going to be 3.40 times 10 to the minus 3. So that is going to be the x that I'm going to move up into my final line. I'm going to change colors so that it makes more sense. I'm going to have 3.40 times 10 to the minus 3, 3.40 times 10 to the minus 3. That is going to be a concentration of H3O, which is great because pH equals the negative log of the H3O concentration, which I just solved, the negative log of 3.40 times 10 to the minus 3. That pH is going to be 2.47 to the correct number of significant figures. And that's good because that's all really that this question was asking me for. So just to remind you, we have to do every one of these steps just to get that pH. And so we've given you the typed out solution so that you're able to take a look at that step by step. And then we've also made sure that you have access to an ice table so you can see what it looks like as you fill this out on your way to trying to get to that final pH of 2.47. So that concludes this lecture, and this should help you with additional problems on homework 14A, and I will go ahead and continue working on the lectures that will help you with 14B.